Well, good morning, everybody. How's it going today? Welcome to Ellensburg, Washington, USA. So glad you're with us again. The local time is 8:52 in the morning, Pacific time, and we will begin our session called Clockwise Rotation at the top of the hour at 9 a.m. Pacific time. That's about 8 minutes from now, so you can scrub ahead if you're watching this in replay. As always, here's to you for joining us. Sunheit. Let me take care of a couple of matters with the technology, and then we will start saying hi to some folks. Yep, okay, did that. And then I do what? That's what I do. That's what I do. Thank you for your patience. Okay. Still not happy. Hang on. I need to see that. And then I need to see that. Got it. Okay, I'm live right now, reading comments. We have 300 watching at the moment, and more will filter in. By the way, before I forget, it's always helpful when I watch the replay to see the live chat, to see what you guys are interested in, etc., your reactions to certain things. And a few of you always kind of, every once in a while, you kind of just write how many people are watching live at that particular moment. And that's interesting to me. So thanks to those of you who have kind of taken the time to do that. You know, this typically, we start with about 300, we're up to 360 already. And then it kind of builds to, I think it's still about 1,000, isn't it? About 1,000 people watching live, kind of in the heart of the session. And then maybe when we're done with the guest or whatever, we start losing folks. That's fine, but I'm just, you know, if only 12 people tuned in, as the alphabet continues, if only 12 people are with us, then I got to change my approach. But it seems like the numbers continue. In other words, our group continues to be strong in numbers, and so that's helpful to me. Okay, good morning. Okay, I guess I do have to go back. Let me go back. I'm back in the live chat here saying hi to folks. Some of these are familiar places. Bryce in Tasmania. Good morning, Bryce. Good afternoon. Sankalp in Rishikesh, India. Hello. Great to have you with us today. Boy, 2 for 2 as far as the distant land bingo card is concerned. Western New Jersey, that's exotic. Hello, good morning. Dan, Nick has never said hi to me. Dan Culver? Culver? Good morning. Anacortes, Washington, that's Chad. I'm back in the chat. Bevan is a ISU grad to another. Hello, Bevan. Idaho State University represent. Carlisle, Pennsylvania, that's Teresa. Phil's in Index, Washington. Pat is in Yakima. Jackson, Santa Monica, California. Cheers. Carol's in Paris, Illinois. Big Ball, 1986 Globe, huh? Culver City, California. Nice and sunny there. Yeah, what is it here? It's 28 degrees and sunny. I guess you win. Phil's in Mankato, Minnesota. Shirani, Littleton, Colorado. Sunny, Oregon, West Allis, Wisconsin, Kent, Washington, Carefree, Arizona, Chelan, Washington. It's always fun. Always fun. It never gets old. Charles is in Hamburger City, Montana. Never heard of it. But I'll put it on my list of places to visit. Okay, I'm going to come down to I'm going to come down to live and we'll say hi to a few more. If you want to retype your name, I'll do that, or your location. I love the location part more than anything. Waikele, Hawaii, I'm practicing. Laka'a, Finland, hello. East Wenatchee, Melbourne, Australia, hello Ian. Fort Dodge, Iowa. Oles in Norway, is that a joke? Deer Park, Washington, it's not a joke, thank you for being with us. Ottawa, Ontario, Canada. Nashville, Tennessee. Kingfield, Maine, I'm just grabbing things as they scroll by. Marysville, Washington. Menominee, Michigan. Western Australia. Perth. Woodstock, Georgia. Kathy in Brisbane, Australia. It's 3 a.m. there. Have a good one. Okay. Well, I just saw many of you yesterday, so I don't know if I have to update you on the last few days because it's been less than 24 hours. And yeah, let's do it. We'll test out the hotkeys here. Oh, I see. Do we have a problem? Oh, we have a problem. Houston, we have a problem. Okay. Something's going on with the iPad. We're not using it today. No big deal. No big deal. Watch stays on. I'm not pissed. That's a tell, man. If the wristwatch goes off, that means I'm not I'm not happy. I'm stressed out, like I was with Aaron Donaghy on Wednesday. The wristwatch came off. The little Velcro. It's like, but yeah, there was a problem a few minutes ago when I set it up, but no problem. It's 2 minutes before we start, so I'm going to just say hi to a few more, and then we'll get rolling. I'll give you a chance to even read the board. I've been blocking your way. Thank you, but I don't need suggestions on what to do with the iPad. It's just gone. Okay, it's just gone in my head. Appreciate the. Where is our guest today? Oh, you want a clue, Kyle? Kyle wants to guess the guest. And I'm not giving you even a hint. Sorry. John Nash reports when he woke up, he realized he had been rotated and transported to the other side of the bed. Spreading reads John, dreaming about geology and rotating and, okay, very good. Bath, UK, hi Carolyn. Hi Carolyn in UK. Ann is in San Diego. People guessing who the guest is. That's kind of fun. Kind of fun to keep you in suspense. I don't know if you've noticed, but after the replay is posted, then I add the guest's name in the title of the show, but I don't do that on purpose. I don't know why. Okay. I got a minute before I got to get rolling here. Thank you for joining us this morning. Always appreciative of your time and energy. I can feel it coming through the monitor, which happens to be alive today. And we will begin in just a couple minutes. Thank you. Hot mic. Okay, now you don't have an iPad today, boy. You don't have an iPad. That's no problem. What was I going to show on the iPad? The schedule. Yeah. What else? Yeah, we don't need that. I really don't need it. Don't need it. Don't need it. Spotted cow. Don't matter. It don't matter. It don't matter to me. One more time, would you mind, before we start? Are we 5 by 5? We're 5 by 5? I didn't even really check. That's how confident I'm getting. Thank you. Okie doke. Good morning, everybody. Thank you for joining us. This is a session called Clockwise Rotation. We are to the letter I in the alphabet. That's not a Roman numeral, that's the letter I. So we've been at it a little while, and we are now arriving in the Eocene as advertised. And our last two shows involved Siletzia. So here's a little warning. We're probably leaving the Eocene today. You're like, what? We finally got there. You said this was going to be a Siletzia show. Well, I'm improvising a little bit with today's show. You know, we did get connected to this concept of clockwise rotation with our guest Ray Wells yesterday. And I want to continue that discussion of clockwise rotation today. But you can see my questions, I think. How far back in time is this clockwise rotation a thing? Like, did the clockwise rotation from yesterday and Ray Wells, did that rotation begin with the docking of Siletzia 50 million years ago? You remember the punchline, don't you? There's been 1 degree of clockwise rotation every million years in the last 50 million years. So there's been a steady clockwise rotation, even today, but it started in the Eocene according to yesterday's session. So I want to know, was there clockwise rotation before the docking of Siletzia? And if so, what kind of evidence would we have? And how far back would we have to go? So I'm willing to go earlier. I'm willing to go back to the Cretaceous. I don't know, even further than that, maybe. I don't know, we'll see, once we get our guest to join us today. But I'm also kind of thinking about the North Cascades. As you know, this series is all geared towards learning new things that I can and then applying it to the North Cascades. And we have not done much yet, not yet, with the details in the North Cascades, but that is coming, especially after the holidays. We will be in the North Cascades in central Washington for most of the rest of the winter. So we're still kind of warming up to that, I must say. But I want to start with my portion of the program, kind of like we did yesterday. I want to do things maybe a half an hour or so. So by the bottom of the hour, I'm hoping to be done with my session, and then we go to the guest. I want to start with how useful and how memorable this clockwise rotation thing is. So what do I mean with that? Well, I've been teaching for 30 years here on this campus, 30 years. And it's not until about, 15 years ago maybe, that I started sharing clockwise rotation with audiences outside of the classroom. Whether that's giving live lectures around the state or starting with the TV stuff and the YouTube stuff. And it involves, this. And my first message is this concept of clockwise rotation. It just grabs people, regardless of the age or the background or how much of the stuff they've seen online. I talk to somebody in the grocery store, they bring up clockwise rotation. It just, and you might have an idea of why that is more than I, but I think it's the simplicity of it, the elegance of it, and how useful and memorable this concept of clockwise rotation is. So can I keep the glare off of this? Probably not. What am I doing? Here. So Ray Wells, Ray Wells data, Merle Beck data, blah, 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 from yesterday. But Bob Butler at University of Portland had some workshops for middle school teachers, and I was involved as one of the I was involved in that program, and so I was gifted one of these teaching boards that I have used over the years. So you see what we're doing here. I'll come in a little bit tighter for you. My windows are screwed up this morning. Oh well, I think we're functional here. So this is kind of a nice review of yesterday and the clockwise rotation, and as you get closer to the coast of California, of Oregon, and of Washington, there is more clockwise rotation than further inland. And so, I don't carry this board around with me and do this, doink, 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 everywhere I go, but it does, you can see there's numbers on here. I think these are millimeters per year, where our GPS network has been measuring this even today. And as we alluded to yesterday, once we get up into British Columbia, this whole rotation game stops. There's a Canadian buttress. You see the stop sign there. that Butler put on this thing. I think Jenda Johnson was involved and a few others. So, we're not going to talk about the evidence for this going on today, I don't think, because we covered that, I think, yesterday. But we know where we're going with this discussion. So, how has that concept of clockwise rotation been useful in my teaching? What kinds of things in Washington geology can be explained really only by bringing in this concept of clockwise rotation? That's what I want to do here on the chalkboard. So I want to go to the map of Washington. I don't think we've even really used this side of the board much for the actual purposes of looking at Washington geology. But that ends today. So I'll do this in storybook fashion, I guess. So it was August of 1992. That's starting to feel like a long time ago, almost 30 years, right? August of 1992 when I set foot for the first time in Central Washington. Liz and I had our first baby boy, 6 months old, and we quit our jobs in Ohio at the end of the school year. My dad thought we were absolutely berserk and nuts and crazy to leave our good jobs and go out to the west where we didn't even have a job. We stayed with our in-laws in Pocatello for, most of the summer, trying to, there's no email and internet, sounds like writing letters back and forth. Anyway, got hired here with a half-time position. Made $12,000 the first year that I was here. And Liz was hanging out at home with the baby. So it was a rough beginning, or a very humble beginning here in Ellensburg. But I bring this up because my first class to teach was co-taught by a guy named Robert D. Bentley, who had been here for 20 years and had been studying the geology just south of Ellensburg. So Ellensburg's here, and there are these amazing thrust faults. South of Ellensburg, between Ellensburg and northern Oregon, there's a whole network of these thrust faults, part of the Yakima fold and thrust belt. So there's not only thrust faults, but there are folds, anticlines in other words. So if I have to draw you a quick cross-section, should I do it here? Oh, why not? So if this is south and this is north, and it's a sunny sky, and this is not on the map now anymore, this is in cross-section, I'm trying to show you what it looks like from the side in the Yakima fold and thrust belt. We have these significant thrust faults. Where you're taking portions of the German chocolate cake. So in other words, this is pretty young. This is less than 16 million years old that we have this area of thrust faults and anticlines, let's say. So the general idea is, well, here's the main punchline, first of all. So this is a compressional scene. To get folds and thrust faults, you need to squeeze the crust. And you take portions of the German chocolate cake and you shove them up a thrust fault, and as you shove them up a thrust fault, they knuckle over. So the north sides of these ridges are steeper than the south side. Menashtash Ridge, just south of Ellensburg, which I could see walking to school here this morning. And the Horseheaven Hills, and Umtanum Ridge, and blah, 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 okay? Toppenish Ridge. So when I was out with Bentley, and Bentley was an amazing geologist and had done a lot of field mapping in association with the Shell Oil Company in the summers, besides teaching, Bentley had a lot of strengths, but one of his main weaknesses was he could not organize his thoughts. And here I am, I'm just trying to learn place names, like what's that? That's Sela Butte, and that's the Yakima River Canyon. And then I'm just like learning out of a fire hose. This Bentley just like giving all this stuff. Way too much. And I remember regularly that fall, again, I'm new to the area, I'm saying, Bob, why is this area being squeezed in a north-south sense? Here in south central Washington, why are we squeezing the crust like this? Obviously we know it is because we have these thrusts and these folds, but you know, I was just off the boat from Ohio, right? I didn't make any sense. We know the Juan de Fuca plate is subducting offshore in a northeast sense. We got the Pacific plate going northwest. It didn't make any sense. And this is 1992. This is before the internet. This is before the GPS network was installed across the Pacific Northwest to document the clockwise rotation that we now know. And you know that every day we talk about Merle-Beck now. Hell, I should call this Merle-Beck A to Z. So Merle-Beck was documenting for a long time northward transport and clockwise rotation of these Cretaceous basilisks, let's say, but Bentley wasn't talking about Merle-Beck. At least I don't remember him talking about it. So the main thing I remember from that first fall is I kept pushing Bentley, like, I don't get it. Why are we, you know, stop giving me all the details, Bob. Why do we have north-south compression in a general sense in this area? And he's like, put me off, you know, God damn it, Dick. It's movement on the San Andreas Fault in California. And I'm like, what? Movement on the San Andreas Fault is going to explain this? I don't understand. And then he kind of shrugged me off and head off. You know, it's a field class. You just leave and just start walking away. Okay. Well, to move the story along, this department, not Bentley, but Megan Miller and colleagues, started installing a geodetic array called PANGA, P-A-N-G-A, Pacific Northwest Geodetic Array. And installing on all these ridges in south central Washington. It was first campaign style, and then now they're permanent. And then it expands to the entire Pacific Northwest. And to this day, up on the third floor of this building, I'm pointing to heaven. The guy's up on the third floor. Every half a second this morning, there's data pouring in from satellites in space that are communicating with all these permanent GPS stations, and they are showing exactly what the paleomagnetic people were saying for the last 50 years. In other words, and you heard this from Ray Wells yesterday, the paleomagnetic data was right. And it's been backed up now with this amazing real-time data coming in through the air into the roof of this building and then being distributed out through our website. So that's a thing for sure, and it was before I understood that the clockwise rotation is the reason for this squeezing. So it's not really north-south squeezing in a sense. It's the stop sign here, which is truly up here, but as far as northern Washington is concerned, the stop sign is even here north of Wenatchee. And then we continue to drive northern California closer and closer to Canada, and we squeeze and continue to make these Yakima folds. So, why is it so memorable for many people who watch programs when I'm talking about the geology of central Washington? The answer is, there's a bunch of ridges that are 1,000 feet high. I just mentioned them. If I drive south after this live stream and decide I'm going to go shopping in Yakima, what? I go up and over Menashtech, that's 1,000 feet up and down. North Tanum Ridge, 1,000 feet up and down. South Tanum Ridge, you know, they're big structures and you can see them. The German chocolate cake has been wrinkled in the last 16 million years due to clockwise rotation. That's why I think it sticks in people's minds. Okay, well, let's say people don't live in eastern Washington. How about they live in Seattle? Well, clockwise rotation helps understand the geology over there too. Really? How? Here's how. Not Seattle, Washington, and there's a major reverse fault. It's not a thrust fault, it's a little steeper, but it's still a squeezing fault, the Seattle fault, that made a big earthquake, magnitude estimated 7.5, about 1,100 years ago. Created a tsunami within Puget Sound, and there's 20 feet vertical uplift in downtown Seattle about the year 900 AD. That's a whole nother topic, but I'm including the Seattle Fault and the Tacoma Fault and the South Whidbey Island Fault and a bunch of newly mapped faults to give you the sense that, notice I changed the trend a little bit now. Regionally, it's more of a northwest-southeast trend to these faults. Thrust faults here, reverse faults over here, but it's still a clockwise rotation story. So we have seismic risk now. The clockwise rotation is ongoing, and so there is concern about the next magnitude 7 earthquake on one of these shallow crustal faults. And yes, these same shallow crustal faults further inland are also at risk, but as we currently understand it, the risk decreases as you get closer and closer to the pivot point. And our guest can help us with this, but I've always used Pendleton, Oregon as the pivot point for our rotation. And my point here is that, remember yesterday, we have more, what did Ray say? The rate is faster, not the speed, but the rate. The amount of degree of rotation per million years is a higher rate as you get closer to the coast. So in my way of thinking, currently there's less seismic risk. There's still seismic risk, but there's less seismic risk from this clockwise rotation the closer to Pendleton you get, because there's not as much rotation. But out here, the risk gets a little bit higher. What am I doing today? I thought we were talking about clockwise rotation. I am, man. But I'm talking about pretty young clockwise rotation. Let me do one more thing. No, I'll do two more things. Some of you were asking with the Aaron Donaghy show about why the crescent basalt, why the Siletzia basalt makes this big horseshoe. That's kind of a strange pattern. There's been a tacoing of the accreted Siletzia basalt on the Olympic Peninsula. And why do we have a tacoing? Clockwise M&F in rotation. Now, I haven't used that horseshoe, that crescent look of the basalt on the Olympic Peninsula as a kind of tactile result of clockwise rotation, because I think it's a little bit more esoteric. But when you look at a geologic map, that pattern certainly shows up to you, and as I understand it, again, we're rotating, and so we're deforming, or we're making this orocline on the Olympic Peninsula. Leave it alone. I don't know much more than that. The last example of how clockwise rotation can just sweep in on its white horse and solve a long-lived debate with a very simple visual is a paper I have waiting for you. And since the iPad's not functioning well for me this morning, you'll just have to make a mental note. Go to nickzentner.com, upper right-hand corner, click on the word Eocene. You'll find 3 new papers, I think. And one of them is Ray Wells. I think it's 2012, involving the Cascades, the Cascade volcanoes, and something to do with clockwise rotation. Like, oh my God, come on, I'm not willing to go that far. I've been taught since day one that the Cascades are from subduction of the Juan de Fuca plate. Well, I'm not. That's true. That's true. But let's get rid of the rest of this. I'm almost done, by the way, almost done. We're about to go to our guest. I remind you as I erase here that I'm just trying to share the uses of this very powerful concept, which is not just a concept, it's now backed up by real data from multiple angles, paleomag data, GPS data, other kinds of data. So that paper, which is a favorite of mine, Ray Wells, I'm going to say 2013, I think, now that I think about it. 2013, Cascade Arc Rotation, something like that. Old. So I did notice that Ray double majored at Penn State. Our guest yesterday, Ray Wells, double majored in geology and art. And it makes sense to me because many of his papers have these beautiful illustrations that just kind of stick. And you'll enjoy that paper. It's colorful as well. Ray's basically saying this. There's an ancestral Cascades. There are some Cascade volcanic centers that are older, and then there's a line of our current Cascade volcanoes, and those are younger. Do you want some dates? We'll just say Quaternary here. So in other words, our present cones are in this kind of new belt of Cascade volcanism. But there is this older belt going back to the Miocene. So this is back, 16 million years, if you like. And this has been known, after a couple of generations worth of mapping in the Cascades, it's known that we have this older place where the Cascade volcanoes were operating, and they're no longer there. So I'm putting X's where the cones have been snuffed out and they're gone, they're eroded away. And then there's these new things. Well, what kind of tectonic model would we have to explain basically a shift of where magma is coming up in the Cascades? It used to be coming up here, let's say 16 million years ago, and more recently it's coming up here. Why did it jump to the east? Okay, well, if you look at some of the papers, here was the explanation. This is before Ray Wells. This is before clockwise rotation. What do you think? I'm not going to pause and wait, but what do you think? Okay, let's do another cross-section. Sunny day. We subduct an ocean plate offshore. We make the old, I should do it in white. We should do the old volcanic arc here. So 16 million years ago, there was a subduction of an oceanic plate, and there was a certain angle to the subduction of that oceanic plate that created magma, X number of miles inland from the trench, and then here we go. We've got our line of volcanoes in the Cascades. You can just think like the first half, the Cascades go back 40 million years roughly, and so the first half of the Cascade story, from like 44 million years ago until, let's say, 20 million years ago, the volcanoes are lined up here. And then there's this weird shift. The old model said, oh, it's easy. It's easy. We just changed the angle of the subducting plate. Because what do you guys want to do? You want to explain why all the Cascade volcanoes shifted east? In other words, we want to get rid of those guys, kill this magma, and we want to have some newer Cascade volcanoes just a little bit to the east, like 5 or 10 miles. Piece of cake. All we have to do, says the old model, is we take that older angle, that steeper angle, and we just flatten it out. We're good. Job well done. And so you go from old arc to new arc by playing with the angle of the subducting plate. Convenient. But Ray Wells says, you guys, did you forget about paleomagnetism and GPS? And the fact that the Pacific Northwest has been rotating? Ray Wells, 2013, says we can explain this shift not by playing with the angle of the plate. Let's keep the angle of the subducting plate about the same. Instead, let's rotate clockwise. And you're like, I don't think I see it. Give me 3 more minutes. What do I have, white for the old? Yeah. Hang on. Hang on, Patrick. Are those the colors I had? Yeah. You've got the paper to really flesh this out, so I don't want to spend another 20 minutes on it. But Ray says, what if we just keep the avenue of magma coming vertically from a steadily angled subduction, terrible grammar, but you know what I mean. Let's not play with the angle, but instead, let's rotate the crust over that stationary subduction zone. And you can take in Oregon and Northern California and even Southern Washington, you can take what used to be the active arc and move it off of the active arc and make a new arc in its place. Because this is still the hot zone where the stuff's coming up. And to build on it, he said north of Stevens Pass, it's flip-flopped. And we've got the older Cascade arc to the east of the active, which also makes sense with our clockwise rotation. Maybe that works for you, and if it doesn't, you have a paper to enjoy. Wells, 2013. Okay. Do you remember our two questions for today? How far back does this rotation go? And two, how much is the clockwise rotation affecting the geology of the North Cascades? So have you guessed the guest? He's been in the green room. I got to pause for just a second. Volume's off of that. And is volume off of my window here? Yes, it is. I don't think our guest is eating fondue today. Maybe he's been grilling brats out in the backyard, and he walked into the geology building in Madison, Wisconsin to join us. Basil Tikoff.
Hey, Nick.
How are you today?
I'm doing just fine, thank you. And yourself?
Oh, I'm doing terrific. You bet. We have plenty to discuss, and it's wonderful to have you back. I can't see the live chat at the moment, but I'm sure people are very thrilled to see you back. And I don't know. That's all stuff that's pretty recent, right? The clockwise rotation that I've been discussing, not even really going back to Siletzia time. Those are pretty current. So let's go for it right away. Have you been doing work on this clockwise rotation thing?
Yeah, so it's amazing. It's not just Baja, BC, right? Not all the time. So it's, I'll tell you the story, but it's a kind of a funny one, which is we were trying to figure out the Cretaceous, and we just went along, and we had 2 days to kill, basically. And so we had a paleomag drill. We're like, well, it hasn't worked anywhere else. Let's try it here. And then it was like mind-blowing, the results. And it took like 5 years to figure out what they meant. And so...
Well, first of all, how did you know how to do the paleomag?
We do that, yes. I've worked a lot. I've worked with, this was with Paul Kelso, who's at Lake Superior State University. Worked a lot with Bernie Housen at Western Washington as well. And so it's something I've also done. But I'm a little bit more like Ray Wells, which is I'm a user, maybe an abuser of paleomag,
yeah,
and not a paleomag expert myself. So I rely on their knowledge and expertise to try and, but then I sort of understand the tectonics, so I understand where I want to go to understand. So it's a collaborative effort, like a lot of science.
Sure. So what's the setting for this? This is in Western Idaho somewhere that you...
Well, exactly, but it has more implications than that. So so to me, the bottom line story is that there are two major periods of rotation. And I'll be clear that my expertise sort of ends at the Cascades and it goes into the continent from there.
Yeah.
So I'm going to talk about east. So everything from the Cascades east. There we go. That's the territory I feel a little bit more comfortable with.
Okay.
And if it's okay, and it's going to seem crazy at first, is we're going to talk about the Precambrian.
I mean,
And
you are a card-carrying member of the Lunatic Fringe. I guess we can do whatever you want.
might be a founding member.
You're
Who
a
knows?
charter member, yeah. Okay, good. Yeah, let's do it.
So you'll see why the Precambrian structures the continent so that it has the explanatory power to explain why and where those rotations are happening.
Before we do it, am I hearing that that's part of the answer to our first question? How far back does this rotation go? We're going to go back that far?
So that's a great question. So as I see it, there are two periods. Well, there's really three periods of rotation. There's an early Cretaceous, which is so far out that we're not going to talk about. And that's of the Blue Mountains, which is the central Oregon, westernmost Idaho. But the two you care about, there's a big rotation between about 85 and about 45. It's clockwise, and it's about 20 to 30 degrees. Clockwise rotation. And then it seems that there's a big rotation that starts at about 18 million years. So that's going to be a number that keeps coming up over and over again because that's
18.
the start of the San Andreas Fault System. And it's the movement of the Sierra Nevada block. Because, yeah, we'll talk about that when it comes to it.
Good.
But the Sierra Nevada block is also moving north because there's a right lateral shear zone behind it called the Eastern California shear zone.
Okay, so 80 to 40,
85 to 45.
Okay, and then
then
younger than 18.
And then younger than 18. Exactly.
Okay. Well, how do you want to proceed? Do you want to share a screen right away, or do you want
If
to
it's
just...
okay, I think since it's a little bit of a story, but I figure it's Sunday morning, we can have a little bit of a story.
Oh yeah, I got to get my... Oh yeah, let's go.
So we can do that. So I'll share my screen.
Good, and then I'll bring it in as soon as I see it in the green room here. And
all right. Let's see if my fancy two-screen system is going to work for us here.
Sure. Oh God, we got people in the live chat talking about Eldritch Moors and the Lunatic Fringe and...
All right, Nick, can you? I've knocked out my ability to see it. Can you see that though?
It's not in my green room yet.
All right, I'm going to try it this way.
We got time.
Yeah, I think we have time.
Yeah, I guess we should have practiced this part, but oh, there we go. There we go.
All right, now you got it?
Let me bring it in.
Okay, super. So I'm going to do it this way.
He's a Mac user, ladies and gentlemen.
So, Nick, is that sufficiently large to see it?
I think so, yes. What if you hit full screen? Would it still just...
I'm worried if I hit full screen, it's going to knock out both my screens and I won't be able to see you.
This is great. This is great. Oh, yep, that works. Either way is fine.
Okay, that's fine. So now I can't see you, but you'll have to stop me if I blab on. So, in fact, this does come back to Eldridge Moors. And if you look at North America, and so here we have Laurentia in the middle, you can see Hudson's Bay. So if you look at the top part of Laurentia or North America, that's the West Coast. Yeah. And we don't really know what was there. We don't know whether it was Antarctica or Australia. People still argue about. They think it's those two, but how exactly they're configured is what they're talking about. Mm-hmm. So that has to come apart, right? And we know how continents come apart. They come apart on rift segments and transform segments. So in the North American literature, there was this debate. So Karen Lund on the left says it comes apart and it's actually coming apart to the southwest. Bob Speed says, no, it's coming apart to the northwest. And so either one's possible. But we know that it's not going to come apart as a smooth boundary. All right?
I'm with you.
All right. So when you look at North America, though, we have what we think is the old margin. And that old margin is this 706, this strontium 87 to 86 isopleth, just means constant value, of 706. And so everything to the east of that line is old Cratonic North America. It's been around since the Precambrian. Everything outboard, including the entire state of Oregon, is accreted or suspect terrains and stuff that's been added. So that's what we've been talking about. It's Siletzia. Before that, it was the Blue Mountains. So it's all these different things that have been added on. All right. So what we said is, okay, so this is us, two people, Paul and I, with the drill, and we went up to this area. It's not quite where that red line is, but it's close. It's right up here. And we said, there's some 85 million-year-old grants. We didn't know the age at the time, but we said they were young. they're 90 to 85 million years old, and they've cooled by about 85 million years. And we know that the Blue Mountains, so this accreted terrain here, these are the Blue Mountains of Oregon, and they sneak into westernmost Idaho and a little bit into Washington State even. And we know those Blue Mountains terrains have added on to North America. People talk about when exactly. But we know from paleomag on some of these big plutons in here, the Wallowa batholith and so forth, that they've rotated 60 degrees clockwise since about 130 million years.
Since 130, okay.
We know, this is Bernie Hausen's work, working with Becky Dorsey, and this is from Mitchell, so that would be off the screen on the left diagram. But we know that they've rotated about 38 degrees since 90 million years. And then we know they've rotated 15 plus or minus 10 from about now 45 million years. And that's the work in the Clarno area. So that's around John Day, Oregon, right? So we know that there's this sort of tracking of when things rotated through time. But the question is, what about North America? And has North America rotated? Because, what I should say, things that are on the west coast, so again, west of the Cascades, they're going to rotate more.
Yeah.
So that's Ray Wells' world.
Yeah.
So there's things that are going to rotate more. But to do rotation, you have to look at it compared to something. So we're looking at it with respect to Cratonic North America. But right here, we're on the margin of North America. So maybe parts of North America have rotated. And this is Paul Kelso drilling, in fact, these exact rocks. And when you look at these, and all you need to know is that basically, when you look at the North American rocks, just by Orofino, everything is pointed straight north in the paleomag. But they should be rotated 30 degrees differently from that. And that's work from Bernie Hausen and others looking at the orientation of those poles. And you can choose different poles, so it might be 20 degrees rather than 30 degrees. But the point is that this part of North America right here has to have rotated 30 degrees since 85 million years with respect to other stuff in North America. Is that making sense?
It does. Now let me pause you for just a sec. So I don't think this will derail you, but why were you drilling where you were drilling, and what were you expecting to find versus what you ended up finding?
So we had spent like years trying to figure out the north-south orientation of the 706 line. So if you go in that diagram and you look south of Orofino, this zone, right, it does this crazy thing. People in Idaho call this the dog leg, where it goes north-south and then it bends east-west. And that's just weird, right?
Yeah.
And so we had spent all our time on the north-south, and we're like, well, we haven't gotten anything to work. So then we tried and it turns out there's a particular, this granite had a particular kind of magnetic mineral carrier that carried what we call the remnants. And so it was a really good marker. It was a really high fidelity marker that had to have been magmatic in origin. So.
Okay, good. Thank you. So back to the story. So you've got some rotation.
So you got some rotation. And so it's like, okay, and you know when it happened because you know how old the granites are. So we said, okay, let's just take this at face value. What that means is the north-south portion of the Western Idaho Shear Zone, which is really the continental margin, they're the same thing, wasn't north-south, it was northwest, but really it's that what is now the east-west margin up by Orofino started in an 060 or in a east-northeast orientation, right? And so the whole thing has to rotate in order to make this work. Right? And then you're like, oh my goodness, okay, how in the world are you going to do that? Well, you've got to do anything, you have to have something to move it, which we'll talk about. You've got to have a pivot point, right? And you've got to have a structure that can accommodate it. So the structure that can accommodate it is the only thing big enough is the Lewis and Clark line, which we'll talk about. So this is this big trending zone. It goes right through Missoula, Montana. And in fact, I-90 runs along it, which is to say I-90 runs there because the Lewis and Clark line is there.
Cool.
And so it's this left lateral shear zone, and that left lateral is the hypothesis is that it's allowing this clockwise rotation. It's pivoting at the Snake River. So the Snake River is one of the transform faults, the Precambrian transform faults.
Wow.
So Yellowstone hotspot is following a transform fault.
Seriously?
Yes, and there's lots of issues associated with that. For instance, the Yellowstone hotspot's traveling too fast. It's going twice the speed of the plate motion. So it's your flashlight and tracing paper kind of works, but it's like it's really moving that flashlight. So there's some issues here. It's about twice as fast as it should be in round numbers.
Really? I never thought of that before. Wow.
Yeah.
Cool.
So anyway, so this thing rotates, right? And so you're like, all right, that's fine, that rotates. What that means then is Karen Lund was right, basically, and you'll see why, that this had to have been oriented like this, right? Just like she's picturing it, but then it has rotated into position.
Mm-hmm.
And she used markers in basically along the Montana-Idaho border. So those probably haven't rotated, but the central part of Idaho has rotated. But if you're rotating the boundary, it's not just North America that rotates. You've got to take the Blue Mountains with it. And so what that means is they have to have a geometry where part of this stuck out a little further. So for the lack of anything better to call it, we called it the Palouse Promontory.
I like it.
Right? Because you can't have a northwest Precambrian extension if you have something sticking out to the south and west. You have to have Lund's model. Right? So that's fine. And so what rotated? And I think what rotated is the Blue Mountains plus this little bit of Laurentia. And all of this is rotating, and it's rotating 30 degrees. That's what the paleomag has. And it's pivoting on the Snake River transform.
During Baja, BC.
Well, so I was going to go the whole thing without saying the words Baja, BC.
Well, we can do that.
But you can do that.
I'll honor your request. Let's stay away from that today. Good.
So we'll get to that. Basically, there's only one thing that could move this, which is the insular terrain. Right? And that's fine, because even if you're like sort of lukewarm about Baja, BC, let's just go there.
You can't hold it. I'm sorry. I nudged you.
It's fine. So if you go to 100 million years, Sandra Wild and colleagues basically said, where is the insular terrain? And it restores to at least northernmost California, southernmost Oregon.
Yes.
Not that Oregon really is there as an entity, which is the entire extent of this thing called the Wiz, right? So the movement of that north could rotate it, because what's for sure is even if you just restore the fault, the insular terrain's outboard. If you take the paleomag instead, the insular terrain restores to Mexico, but it's not a small thing. It's a big thing. It goes at least up to, well, again, here's the Western Idaho shear zone. It goes to at least Idaho. So no matter whether you're a sort of a mobilist or a fixist, it's in Idaho. So it's the most likely thing to have caused the rotation.
Yeah.
Is that making sense?
This is amazing. Yes. I mean, come on now. You can do anything you want here. Do you want to continue with the story? Do you want to stop for a second and have me ask you a couple of questions?
Let's do that. Let's do that, because then I'll talk about the why the modern rotation makes sense with the Precambrian.
Okay. Well, let's just go back to this for just a bit. We can go back to those in a touch. So I'm torn, because I do want to talk about Baja, BC, but I also just want to talk about this clockwise rotation as a unit. So let me see if I've got a couple of things. So this older rotation, the pivot point is not Pendleton, Oregon. No way. That's the younger, that's the less than 18 million year thing. Or what pivot point do you like for the younger than 18 rotation?
Okay, so that's where I was going to go next. The pivot point is Orofino. It's not Pendleton. It's Orofino.
Okay, put that on hold. Another one is, I guess it is Baja, BC related. So you showed up in Western Idaho 25 years ago and thinking that you might be able to find some kind of major Baja, BC fault. that everybody's been looking for, essentially. And you run into this dog leg. Is that why part of the reason you got off of that being a major Baja BC fault?
That's exactly right. You can't find the fault north of that dog leg. So to go back.
Yeah, I'll get it. Oh, can you bring it in? No, I guess I have to. I don't think Ray liked he wasn't in charge of controlling the screen. There, okay.
So it's right. You have this big shear zone coming up, but the problem is the shear zone doesn't stop. And this is work by Keegan Schmidt and others. It just keeps going right around the bend. It's hugging the 706 line, right? It will not go. And so what I realized is that, wait a minute, the continental margin is stopping this shear zone from forming. Like, it's deforming the whole margin of the continent, but you can't actually push things into the continent. So that's this figure here, right? That it won't push things in. The way you push it in is you reactivate a pre-existing feature. We think this is the Lewis and Clark line's about a 1.5, and then you push it. So you're going to see why that's important, because, right, North America sticks out, which means stuff can't go by.
Yeah.
But what happens is the insular train is going to push this thing out of its way.
Well, let's keep rolling then. Let's keep rolling with the story. This is excellent, Basil, as always.
So we actually don't know. So I'll tell you all the problems. This is a hypothesis.
Oh, yeah, sure.
Right? We're not sure. We think it rotates on the Snake River transform because that's where the Western Idaho shear zone ends as a north-south boundary. Yeah. But also, it's North America. So again, it's hard. It's rigid. Right? So that can be the pivot point. There. Right. We don't know how much is rotating. Like, we don't know how far into Idaho the rotation goes. I assume the Blue Mountains are rotating with it. And the paleomag of the Blue Mountains is perfectly consistent with this rotation, right? And moreover, it explains how you rotate the Blue Mountains, right? Because you're basically rotating it on this up to 45, but then you're stuck, right? Because there's no more deformation and no more left lateral movement on the Lewis and Clark line. It's stuck. So after that, it's only the Blue Mountains that rotate. So this last 16 degrees of rotation is going to be Blue Mountains only. North America is going to be fixed.
This is great. How do you want to proceed?
Let's go to the Blue Mountain rotation, I think.
Good.
Is that all right?
Yep, absolutely.
Okay, so if we go to the Blue Mountains, so this is work by Rob McCaffrey, and he's basically going to use geodesy, and he's going to say this Oregon block, which he's modeled as a bunch of different blocks, and again, worry about these near ones. The coast is going to maybe do something else, a little bit more.
Yep.
Right, so that may or may not help. But what you talked about earlier was this diagram, which is the geodesy, right? And when you look at this, you say to yourself, all right, where is that rotation axis, right? Because it's basically a big swirl, right? And the center of that swirl is something like this. It's somewhere up in here.
Yeah.
Right? It's certainly in western Idaho. And so when you were talking about the Yakima, it's like, but why? Why is it there? And the answer is the Precambrian boundary.
Oh.
Because the Precambrian boundary, right, this is the rift segment here that goes through McCall. This is the transform segment that comes out from Oregon. The Blue Mountains are the lever arm, like on a pinball machine. The pin is in this Precambrian notch. The ridge with the ridge transform hole is basically going to be the center of rotation. And then that's my best attempt to put the latest GPS pole of rotation on there. So the Blue Mountains is a pinball stip, right? And so everything north of it is your Yakima fold and thrust belts, right? And it's the Seattle Fault, and it's all that crazy stuff. But to do a pinball, you have to shorten in front, but you have to extend in the back.
Yeah.
Right? So you can take a cross section, and you drew this in your indomitable way earlier, and that's a cross section north-south through here, through the Yakima Fold and Thrust Belt. But if you take a cross section through Hell's Canyon,
You son of a bitch! You're involving Hell's Canyon in this.
well, it's the same thing. It's the same. They are literally the same basalts. They're the grand rhomb basalts here shorten,
Right.
and they're shortening north-south. And here in Hell's Canyon, they're extending east-west, the same basalts.
Wow.
So, and then just to do this and show you two different transects, if you go up here, there's actually a big normal fault in Hell's Canyon. And for the people who are not from North America, the biggest canyon in the U.S. is not the Grand Canyon, it's Hell's Canyon. It's deeper. And it's right on the Idaho-Oregon border. And sometimes it's not, you don't get a big fault there, but the whole region has this sort of wide, it's sort of a fan. And the closer you get to Orofino, the less and less extension you get. And if you're in the Yakima Fold and Thrust Belt, as you go towards Orofino, the less and less contraction you get. So Hell's Canyon extension is really the twin of the Yakima Fold and Thrust Belt, all of them explaining this basically 16 degrees, this 1 degree of rotation since about 16 million years ago.
So where was your pivot point from the earlier rotation? Down by Boise or further south?
It's probably further south. So if you go to, if you look at a map of the Precambrian, I'm going to see if I can pull that up quickly. If you look at now the Precambrian and you have ridges and transforms, the next transform is the Snake River transform. These ones, the one down that goes from Nevada to California, that's the Mina deflection. But these seem to be in their correct orientation, the Snake River and Mina. So you haven't rotated them.
Yeah.
You only rotated stuff north of the Snake River transform. So my expectation, and it's only a hypothesis, is that the rotation is pivoting on the Snake River, which means this area is going to get messed up, right? You can't not follow that up.
So isn't the elephant in the room why the rotation is happening to begin with? What's driving the rotation?
Well, okay, now that is a great question. You asked that of Ray yesterday. And it's hard. So basically, Tanya Atwater in 1970 wrote a great paper where she was able to connect the the spreading centers in the Pacific Plate offshore California. And in probably the most important piece of work in Cordillera and tectonics, was able to say that basically the whole system is a right lateral system. It's an obliquely divergent right lateral system early on that becomes an obliquely convergent, but it's basically a strike slip system. And so that is really the start of it. But the rotation of, okay, so now we have to talk about which rotation. We're talking about the Miocene to present rotation. We're then talking, so if we're talking about this rotation, as you said, this is driven almost certainly by this Sierra Nevada block. It has this big dextral fault on its backside, the Eastern California shear zone system. And the pivot point is probably in Orofino. The Blue Mountains are the lever arm that basically hold it out. So the elbow is fixed. The elbow is Orofino. The lever arm is the Blue Mountains. And then the Sierra Nevada is what's pushing it up. So that is probably how that system was. And it's basically coupling of the Pacific Plate to North America, or at least for the rotations on the coast of Oregon and Washington, it has to do with the oblique subduction of Juan de Fuca. So that's the young one. The old one has got to be the insular terrain. It's the only thing, right? Because here, you're not moving in accreted terrain. You're not moving a little blob on the edge of North America.
Right.
You're moving North America, right?
Yes.
You're doing that. And that's why the Lewis and Clark zone is such a big deal, because it's never made any sense to me. But the Lewis and Clark line divides Canadian style tectonics from the Laramie block uplifts. They are bounded by the Lewis and Clark line. And it's like, you can't run an accreted terrain, and where there's plenty of accreted terrains that run into Canada, but you're not doing laramide block uplifts.
Yeah.
Here, you've actually taken North America and you're running North America into North America, basically, along with the Blue Mountains. And that's probably why you're doing it.
Okay. I mean, I got one more, and then you can do some finishing touches, and then we go to the live chat if you're okay.
Sure.
The older rotation story is brand new to me, like in real time. And the younger rotation, we know our plates offshore. We've got the Pacific going northwest, the Juan de Fuca plate going northeast generally. In a weird way, can this older clockwise story say something about what the plates were doing offshore?
They were unambiguously moving in a right lateral sense, right? You can't, if you move things sinistrally down the coast, you would rotate counterclockwise.
Right.
So you can say they're rotating clockwise. Could you do this all with oblique subduction? I don't think so, because there's plenty of oblique subduction, but you get the strike slip systems in the arcs when you do that, things like Sumatra.
Yeah.
To push something so far in, it probably wouldn't work.
Oh, man. You've come through again. You've done it again.
Well, I'm not so sure about that. So can I give you one more wrinkle?
Good. Put some finishing touches up.
The one last touch here is if you buy the accreted terrain stories, now I am going to talk about Baja BC.
There you go.
Oh, this is too busy. Basically,
Let's go full. Can you go full screen on this? Give us
sure.
a little bigger chance to see.
You know what? I'm going to go. I think this is going to be easier to see this on.
Okay. Yes, great.
Right? Here is the so insular is offshore. I'm going to take Sandra's picture because, it's hard to disagree with this, even if you don't like paleomag. Here's the intermontane terrains.
Yeah.
The intermontane terrains also restore to base almost northernmost California.
Okay.
Right? And that's exactly what the paleomag says, that these things have traveled about 1,000 kilometers in round numbers. So as you move not just the insular north, but the intermontane north, you open up a hole. And that hole is going to be right here. And that hole is where Siletzia is going to fit in.
The embayment?
The embayment itself is probably caused by the movement of these terrains northward.
This is a kitchen sink show. Everything we've talked about is in this story. It's amazing.
Well, it's because you don't take just pieces. You try and look at the whole thing, right?
Yes.
It's the Precambrian actually matters when you start looking at the history. And so Siletzia, Yakutat probably would have been happy to stick around in Oregon too, but there just wasn't room in the inn, right? So it has to go. And so I think the reason it sticks around rather than subducting is there's basically a place for it to fit that pulls the subduction zone out to a more consistent orientation. That may or may not be true, right? That's also a hypothesis. But the point is there must be sort of a hole here that at least in part is the movement of these terrains north. But in part, remember, is also the rotation of that Palouse, that Precambrian promontory, way out to the east, right? The question's always been, why is that margin of North America in Idaho rather than sticking out somewhere in Oregon? And the answer is it's probably been pushed in.
Yeah, I see a few in the live chat want to see that chart that you tried to put on for a second. Would you mind? You're in full screen. Can we go back to that compilation diagram?
Sure. Oh, got too excited there.
Oh, join the club.
Hold on. There we are.
There.
So, right, this is Baja BC, which I didn't think I said I was not going to talk about. But basically, there's the insular terrain coming in, hitting at 100. Right, and then it starts to move north. It forms the Western Idaho shear zone, right, as in the arcs as well. It's not just there. There's also 100 million year old shearing in the Sierra Nevada. That's also right lateral and transpressional. That's work like Aaron Yoshinobu, working with a graduate student named Kruger. And then it basically comes up, but then you get stuck up here. The Blue Mountains get stuck. They get pushed in the Idaho segment, whereas to the north, everything just kind of moves north.
This is part of this new paper that's in review right now?
That's right.
You're comfortable?
But what I was really trying to show, and this is the only paper I had that had it, is the Columbian Bayment. Because the intermontane terrain was down here. So this is the 65 million year old thing, but it has pulled north and it has left a hole. What's interesting is there's little bits of the intermontane terrain even down in northwest Nevada.
Huh.
They're just little pieces of it, but then you've got nothing. Then you get the Blue Mountains that are kind of stuck in there, but there's basically a hole. So Siletzia has got a place to go.
So you're not necessarily wild about Ray kind of having a catcher's mitt and saying part of the embayment might be from the collision of Siletzia itself?
No, I think he actually could well be right about that.
Okay.
But you had a very Wisconsin deer hitting a deer analogy, right? But the point is the car is concave,
Yeah.
right? That there's kind of a scoop shape for it to go in. I actually think that's not incompatible, but there is sort of it's not a lithospheric hole, but there's basically there's an indentation in the margin left by these northward moving terrains.
Whoo, baby. Okay. I've hogged your time. I want to get our viewers involved, and you can maybe see the chat now as well. I don't know.
I'll
it's your call.
Out of this.
My God, you are really something. I'm going to scroll back. Yeah, it's time, viewers, to I don't know how many we got here, about 1,000 maybe, and uppercase, if you're new to us, that's how I can kind of see that you're asking a question. I'll get us started, Basil. You got a few more minutes, Basil?
Yeah,
okay,
sure.
Thanks. Ricky Z-Man asks, is the rate of rotation related to the Juan de Fuca to Pacific plate change as it meets the North American Craton? You want that again? Is the rate of rotation related to the Juan de Fuca to Pacific plate change as it meets the North American Craton?
It's an interesting question, actually, and I don't know the answer. I think the Sierra Nevada, right, so Orofino is going to be here. Got to go with this. The Sierra Nevada is going to push it up, and it's going to pivot at Orofino. I think it's probably Pacific North America down in California.
Yeah.
And just to be clear, it's Pacific Sierra Nevada block, because the Sierra Nevada block is separate from North America, and it's moving differently than, say, Salt Lake City, right, which is more fixed to North America. So the Sierra Nevada block is sort of its own player. And so in that sense, it's probably more related to that. Again, what's happening, though, with the Juan de Fuca plate is that it's a free margin, right? It's easy to push a subduction system out, or at least that's how we think about it. So it's kind of, you can escape that motion out. And I think Ray talks about that in his models.
Carol asks a similar question to what was asked yesterday, but we'll try it with you too. Do we know why the rotation stops in Canada? I assume she's talking about the more recent rotation.
I think Ray answered that yesterday, and I'm trying to remember exactly how he phrased it. But again, since you're pivoting on that point, or if you can't basically get it out, there's sort of a limited rotational out, and the Canada is a backstop. So basically, it's not going to deform very much north of there. And if you don't deform north of there, you push all the deformation there. So that's the Yakima fold and thrust belt.
Good.
So basically, the Yakima fold and thrust belt is like the shock absorber, if you want, which is why it doesn't propagate into Canada.
Just for the record, I like your pinball thing. I used to call them flippers. Like, is that what
That's
you call
probably
them?
what they're called. I was never very good at it.
I wasn't either, but maybe our viewers know exactly the right phrase. But it took me a while imagining the whole pinball machine, and then like, oh, we're just talking about the
flipper.
Yeah, the flipper. Yeah. Kyle asked, does the Western Idaho shear continue into Utah?
No. That's the fascinating thing. It seems to end at the farthest south we can find it is in the Owyhee Mountains in southwestern Idaho. There's no equivalent structure. What's interesting is it's an arc. And so as you go south, there is some arc rocks of exactly the same age. Sarah Trevino is working on those. They have right lateral shear zones at 100. If you go south of that into the Sierra Nevada, there are right lateral shear zones at 100 in the arc. And as you go south, I mean, the right lateral seems to start at 100, and it seems to be preferentially in those magmatic arcs, which makes sense. I mean, they're weak. They're basically magmas.
Yeah. Feel free to grab one if you can see what we're doing here. I'm down to pretty close to live now. Oh, well, you can try this one. I think you kind of had your disclaimer at the beginning. Oscar in San Diego, how does geomagnetism compensate for magnetic pole drift?
That's a great question. So what you're doing is you're comparing, okay, there's two kinds of drift. One is the drift that happens about one every 20,000 years, and it's the movement of the, again, the right place, the movement of the north of the magnetic North Pole around the center of the spin axis of the Earth. That takes round numbers, 20,000 years. Secular variation is a name that's used for it. And you do that by taking multiple beds and averaging those beds. So, for instance, granitic rocks cool over a long period of time is one way of doing it. Or you take a stack of basalts rather than just a single basalt flow. So if you're doing basalts, you need like 8 to 10 basalt flows to get a single one data point. Sedimentary rocks, average it, again, as you take a whole series of beds. So that's how you get around the secular variation problem. The rotation, because of the movement of the continents, you do by comparing outboard accreted terrain stuff to Cratonic North America stuff. So you look at like mid-Cretaceous intrusions in Arkansas. And that's how you find the Cratonic poles. And then you compare them. So that's the, or you can even look at all the different continents and then make models for spreading centers. But usually the best is from the continent that you're trying to compare it to.
I can't hold it. I mean, I think this might be the last PaleoMag session this winter until next winter when we try to really get into more of this. But it's more than just plutonic rocks that we're getting this PaleoMag data, right?
Absolutely.
So it's what's the range of rock types and age ranges that are all kind of telling this elegant story?
So sedimentary rocks are, so again, with the caveat that this is not my expertise.
Got it.
Sedimentary rocks are hard to do, right? Ray was talking about that. You need very fancy equipment. You need field-free rooms. You need to have the right detrital material getting in those samples. But if you do all of that, they're quite good because they average time. So that's why. What you really want are interbedded volcanic lava flows with sedimentary rocks from which you can get horizontal, and you want them to go back and forth through time. That is the Win et al. 94 study, which says 3,000 kilometers of northward transport. That's why that one's so bomb-proof. It's in horizontally bedded units that are interbedded volcanics and sedimentary rocks. So, horizontal, that there's no flattening strain. And it's reproducible. So basically another paleomagnetist named Randy Ankin went in and redid it. And it's like, yeah, that's exactly what it is.
And where were those field sites with that perfect situation?
Those were in southern British Columbia,
Okay.
the Tyouten Basin.
Amazing. Let's do 3 or 4 more. I should have these ready to go, sorry. Clit coast to coast. When the Juan de Fuca plate totally subducts, will the rotation change?
That's a great question. So what will happen there is that coastal Oregon, so what's going to happen is the San Andreas system is going to keep moving north, and then you'll ultimately have a strike slip system through going. So remember, there's a San Andreas system in the north, Juan de Fuca, and then you've got another strike slip system in Canada called the Queen Charlotte, or the fault system. And so the Queen Charlotte, San Andreas will become one. And then you're going to just keep moving material north up the coast until there's a plate change of the Pacific plate. And, who knows when that'll be and why it'll change, but it will.
Okay, well, we are heading to the North Cascades in the next couple of shows, and Pat in Yakima wonders, did the rotation drive the Straight Creek Fault? Now, it's out of your expertise, possibly.
It's possible. It's certainly possible. My problem is, when did the Straight Creek Fault move? I think it might be slightly earlier than that. So I can't say without knowing. If the Straight Creek Fault is moving after 18 million years, I would say probably did, but I think it's an earlier structure than that. I should know that. This is bad. I should know that. I don't.
You're fine. The Straight Creek Fault had action on it between 50 and 35 million years ago.
That's what I recall, but it's older than 16.
Yeah, yeah. Well, during a time when you don't have well-documented clockwise rotation anywhere.
Right, and there's also going to be a reason for that, because when the extension comes in and the extension kicks in at 55, the extension's oblique. The extension is not north. The accreted train's pulling out. The accreted trains pull out to the north with a right lateral sense of shear on them.
Mm-hmm. Well, that's our time window really for the rest of the winter is 60 to 40 million years. And speaking of which, we formally have not talked about the chalice magmas yet in this series, but Sven asks, could the Lewis left lateral fault be glued by the chalice magmas?
Yes. So the problem, and you're going to run into this, so we might as well just get it on the table. The Lewis and Clark line is sinistral till about 55, and then it becomes dextral. It actually turns around and changes its motion, and it's totally sensible why it's doing that. But it's I don't know whether I want to get into this, but the point is it reactivates in the opposite way, associated with the extension. That's the way of saying it.
Well, I think that's how we'll finish, because I think I mentioned to you by text or something, that's a pretty new thought to me, that you can take a structure, a fault, from a collisional story, and then suddenly it's not a collisional situation anymore, and the thing is reactivated in the opposite sense or a different sense. And in the back of my mind, when we go to the North Cascades and we see certain kinds of faults doing things at a certain time, I guess in the back of my mind now I'll realize, well, how old is that structure, and was it doing something completely different in an earlier time? Do you know of examples in the Northwest besides the Lewis left lateral fault that does this about face thing?
It is a truism about faults that they reactivate. And so you will find that a lot of the shortening structures will reactivate as extensional structures when you get to this. So because everything's collisional in at least the coast ranges, up to, again, it sort of, but somewhere around 55 million years, and then it's going to go extensional. And so they're weak structures, they're parallel, they're going to just keep going. The only thing is, it seems like as I read the literature, the dextral motion continues in the Cascade core longer than it does south of the Cascade core. So in other words, you might get strike slip, I think it's until about 45. Up in the Cascade, so that it's going to go on a little bit longer.
Interesting. Well, come on now. You're 2 for 2 with these appearances, and we all really appreciate your time. I don't know where you are in the semester. Is it finals week this coming week?
No, last week of classes, unfortunately. So.
Oh, God. So you got everything else going on, too. So a special thanks for all that coming in on a Sunday morning. So
it's always a pleasure, Nick.
Thank you, Basil. All right. Well, have a good day. Thanks much, and we'll see you next time, whenever that happens to be. Okay, I got to get rid of you. How am I going to do that? Come on, cursor. Okay, here I go. Goodbye. Well, I hope you enjoyed that as much as I did. Basil Tikoff, University of Wisconsin, Madison, in the late stages of fall semester. I didn't realize they were still at it. I probably wouldn't have bothered him if I knew that he's been working around the clock with his teaching and grading and everything else. I don't have the iPad working. We'll do a few more questions. Let me come down to live. But before I forget, let me write out the next couple of times I'm going to see you, if you want to join us again. What's today? This is session. So we'll do a couple more questions with you, but before I forget, I want to let you know that the next time we will do one of these sessions is back to our normal schedule. So Wednesday, December 15th at 2 p.m. Pacific time, it will be session J, and we'll have another guest. I've already lined up who that is. And I'll have a couple days, Monday and Tuesday, to think seriously about what I want to do with you all and the guest on Wednesday. And then as a programming note, the following weekend will be the last weekend before the holidays that we'll be at it. We'll do one Saturday morning, December 18th at 9 a.m. Pacific, and session L will be Sunday, a week from this morning, Sunday, December 19th at 9 a.m. Pacific. So, most of you are not able to join us live, and totally makes sense to me. And you watch them in replay. I am noticing people are watching these replays, and they're watching them in order. Then the view numbers continue to build. So great to see that. But those that like joining us live and asking questions directly, we'll look for you next time, Wednesday at 2 p.m. Pacific. Vinmans is locked out of the building. Well, Jeff, if you're there, I put a rock in the west door, and that's our little secret entrance. So I mentioned that in the last show. So if, Jeff, you're watching right now, I'm pointing to the little west door. I've got a rock propping the door open to allow you to get in. And if you can get in, I'm not going to go look for you now, I guess, Jeff. Maybe you're watching in real time. I'm going to scroll back and just find 3 or 4 more questions that maybe Basil didn't get to. All this stuff about Vinmans. I don't know how else to do it except spending 20 minutes going to find them outside, and I don't want to do that. Yes, it's cold outside. Oh, good Lord. Vinmans. You got to love it. Papagino, was the pivot point craters of the moon? Well, I hear him. He just got in. Jeff. We'll get him on camera here. Hang on. Hey, Jeff. Hey, Jeff. Hey, Jeff. Come on over. You're good. Let's have you say hi to these guys.
Oh, well.
Come on. Got a special guest. You look right into that camera.
Good morning. I should show these right out of the oven.
Ooh.
Where's all the people?
I don't know. They're not out there?
I don't see anybody.
Okay.
You are going to do
No,
quite
come
well
on,
today.
come on. Talk to. How long you been operating the bakery here in town?
Coming up on 7 years.
7 years.
Been there 20.
And have you had people from our series in the live chat drop in over the last year or so?
Quite a few. Over this summer, there were quite a few out-of-towners that came through, and they would always say something, and it was always great to see them. It was just like instant friends. So I love the Zentner crowd very much. Been good to us.
You're not normally in on a Sunday morning.
No, I had a little work to do for the TAV. They had biscuits and gravy this morning, so I thought, well, I'm here. I'll make some cinnamon rolls and run them up to you. But if nobody else is here, you're going to be taking all these home, so sorry about that.
Well, they must be somewhere. Okay, well, I'll make sure they get to them. Well, thank you.
Thank you.
Okay.
Just leave them here.
Thank you, Jeff.
I gotta go.
Okay. See ya.
See ya.
Appreciate the effort. K is the Sierras. Are the Sierras still affecting the current rotation? They're part of the rotation. I'm still a little confused on what's driving the rotation. I'll stick with kind of the way that I've been teaching it, I think, which is realizing that these offshore oceanic plates are driving that. But I think I'm missing something in that story. Live chat's frozen. Let me get down. Now I'm coming all the way back. We'll do 2 more. It's almost 10:30. Oh, it's all Binman stuff. Okay. A toast to you. And a toast to our guest, Dr. Basil Tikoff from the University of Wisconsin. Here's to Basil. A toast to you and your health, your mental health, your physical health, and the well-being of all who surround you, family and friends. This continues to be a very polarizing time worldwide. We don't need to get into that, but I mention it because there's a decided effort here to avoid that, even in geology, to avoid the confrontation and the good guys and the bad guys. But of course, the subtext is, it feels like everything is good guys and bad guys now. And I'm sick of the extremes on both sides of any issue. I'm just tired of it. I don't know where you are. I'm just tired of it. So let's get away from the fringes. Let's get away from the edges of this, the polarizing extremes, and let's just embrace the commonality that we have. I regret even saying that. Here's to a polarizing comment, perhaps. I'll hear about it. Here's to us. Last comment. I've mentioned this off and on over the last 2 years. I'm getting about 100 emails a day, and I just can't reply to all those emails. And I see them all, I read them all, I just don't have enough time to reply to all that stuff. And so this is the most efficient way for me to say thank you for the time to write, and I'm genuinely sorry that I don't have the time to reply. Now, if there's a geologist who I'm emailing with and potentially joining us here, then they take priority. I'm sorry. And I try to reply when I can, but there's just not enough hours in the day. Okay, I did the toast. I'll figure out what happened with the iPads, probably an easy fix. And thank you. I love you. And we'll see you on Wednesday, 2 p.m. Pacific, for session J of that crazy Eocene A to Z. Thank you. I love you. And goodbye.